Hi, good morning, good afternoon, good evening, everyone. Thank you so much for joining our second webinar on Kinetis FlexIO. This one is part two, example projects using FlexIO. And I'm joined today again by two leading experts in this area, Donnie Garcia from NXP and Adam Benzion from Hackster.io. Let me go ahead and turn it over to Adam for some opening words.
Great. Hi, good morning, good evening. Thanks very much for the intro. This is Adam Benzion, and I work at Hackster. I'm happy to see everybody on the call today. So for those of you who did not participate in last week's call, this is actually a second webinar. It's going to be recorded. We're going to share the recording with everybody if you want to actually check it out again at a later date. And as you just heard, we're actually going to go over some real-life examples and some real projects using FlexIO today. As well, this week, we're going to upload for the first time a sample project with schematics, source code, full descriptions, and components of how to actually build your first Kinetis with FlexIO projects. And also throughout this call, please feel free to use the little chat box to ask questions. I'll make sure I take really good notes, and at the end of the call, we can actually open the webinar to questions for Donnie, who is the expert. So thanks again for joining, and without further ado, I'll hand it to Donnie.
Okay, thank you very much, Adam and Kathleen. Again, whether you're joining live or you're listening to the webinar at a future time, I'm really excited to talk to you about this peripheral we have in the Kinetis line of MCUs from NXP. My name is Donnie Garcia. I work on Kinetis MCUs for NXP. And for this session, this part two, example projects, the goal of this session is really to equip you with some tools, some practical examples on how to use the FlexIO, how to even get started now, even before you have a board. And so it's so exciting to see all the ideas being posted on Hackster.io. And we really want to get some focus and some work on this peripheral, and this session will help you do that. So just a quick recap on what we talked about last time. So on the first part of the webinar series, we learned about problems in embedded design that FlexIO is designed to address, whether it's time to market or power efficiency. We talked about just the environment we live in with embedded designs and how to address those things with the FlexIO. We went deeper on the timers, shifters, and triggers, and we showed how to transmit or receive data. We also went through how logic and state machine modes can work, and we talked about the solutions that we have as part of our Kinetis SDK, whether it be I2C, SPI, UART, or camera software. We showed you where you could get those. And so, again, for this session, we're going to go a bit more in detail and give you some direction on how to get started now, whether you have a board or whether you do not have a board. By the end of this session, you should be able to go through, download the Kinetis SDK, and begin developing if you're participating in this contest. So again, very, very excited. So where do we start? And the first place that we direct you to go is this website here, www.nxp.com/ksdk. And so Kinetis SDK, this is our software development kit. And this is where we have in one place all the middleware, the stacks, the drivers, everything you need to work on various Kinetis MCUs, whether it be the K82F, the MCU that this contest is focused on, or other Kinetis MCUs. This is an essential place to start. So if you follow this website, you will see a button for downloading the software, and that will direct you to another page where you can launch something that's relatively new for Kinetis SDK, and that is the SDK Builder. And so we've consolidated all our tools, our software enablements, into this Builder environment to allow you to customize what you download from NXP in order to create your software. And so after going to the SDK homepage, you will click on the download button, and you'll see these two options here. First, for the recommended software and tools, we want you to utilize the Kinetis SDK Builder, and you can download that. And then this will direct you to another page where you can build an SDK. So again, why is the Kinetis SDK so important? All the drivers and examples and everything we've been discussing that's already been created for the FlexIO is available here. And the goal of these first few slides is to show you how to access that information. So what does building an SDK look like? You will, when you go into the SDK Builder, you'll have the option to select a new configuration. And so if you look at the top of the SDK Builder, there will be a pull-down tab, and you can direct this pull-down tab to select new configuration. And then within that new configuration, it will allow you to select a board. And so this contest is, the platform for this contest is the Freedom K82F. And so after selecting a new configuration, when you select the actual processor to utilize, you can go to Kinetis, boards, and you can see here there's a board option just for the Freedom K82F. So what this does with the new SDK Builder is allows you to get only the pieces of software that are relevant for this hardware. And so there's also some other options around tool chains. And so when you select the Freedom K82F board, you'll have the opportunity to select also the tool chain. And we provide support for various tool chains, whether it be IAR, CAL, Kinetis Design Studio, Italic, or just GCC tools. You have these options, and then once you select your tool chain, you can build the SDK package. And so again, a lot of direction here, a lot of web links and so on, but the main goal is to just get you the software you need on your PC or laptop in order to utilize the FlexIO. And so when you do build the SDK package, there is a building time. So this is a great time to grab a coffee or take a little break. But it'll take some time for that package to be built. It takes up to 30 minutes because it's being built in the background per your specifications. And so a lot of steps here, but again, really important in order to leverage the work that's already been done on the FlexIO, in order to get the I2C, the SPI, the UART, or camera drivers that we have done, this is the place to go. And so definitely want to leverage these steps in order to get that SDK package. And so once you have that SDK package, it will come with documentation and access to all the examples and drivers. We mentioned these on the Part 1 webinar when we introduced the FlexIO, but it's worth mentioning again that the FlexIO peripheral itself has a driver with the APIs mentioned on the right, whether it be setting the configuration of the timers or shifters and defines to help you understand how to use the FlexIO within the software framework. All of this is available once you have downloaded the SDK 2.0 package. And then utilizing this FlexIO driver are modules. These modules implement a camera driver, I2C master, I2S, SPI, and UART. So take the time to download the SDK. It's downloadable at no cost, so whether you have a board or not, you can go and get this software and even begin developing with the SDK 2.0. So very important steps in order to enable you for this contest. So I want to showcase a couple of examples. And this example, it actually is a special case in that it is not in the top folder directories that I showed in the previous slide. In the previous slide, we talked about examples that will be in a folder labeled FlexIO. But this example is pretty unique in that it utilizes our USB driver. And so if once you download the SDK 2.0, you'll see in the boards directory for Freedom KD2F USB examples. And so the reason, one important reason why I'm highlighting this is you may not think if you're working on FlexIO to go and look at USB examples. But we do have this USB example for a video device. And so what this is a great enablement for is maybe your strength isn't on the deeply embedded side and you want to develop some innovation using USB camera data. Well, you can still enter the contest, you can still put your ideas and leverage PC or Windows software to take in this camera data that comes from the FlexIO. And this is the example that you can utilize to do that. So in this README file, you can see that we have created a USB video class device for the FlexIO. It requires that you obtain an OV7670 camera module. These are available in many, many places. If you just search for the OV7670 camera module, you'll see you can purchase it. It's around $8. And once you have this camera module and you solder it onto the Freedom KD2F board, you can easily create this example that shows how to get video data into the PC. And so, again, a key reason why you would want to utilize this is if you have some strengths around processing USB data on the PC side, then you can use this example as a great starting place for your FlexIO contest entry around vision or performing some operations based on camera data. So another example I want to showcase, just because it is very easy to reproduce, whether you have a camera module or not, you do not need any additional hardware for this example. And this is the FlexIO read accelerometer value transfer. And the directory is shown here under the title of this slide where you can find this example. And again, this is supported by a README file that gives you all the information you need to see the FlexIO in operation. And what this demo does is it will take in I2C data from the accelerometer that is on the Freedom KD2F board already and show that data through a terminal. And so this is a great demo in that it is a nice framework, whether you're interfacing to the onboard accelerometer or if you're adding any additional sensors off the Freedom KD2F. This is a great demo to leverage in order to do that, and we'll demonstrate that in the coming slides, interfacing using this same demo software to interface to different types of sensors and what you can do with that. And so again, a very nice demo as an example. If you go to this folder, the Freedom KD2F /boards / Freedom KD2F driver examples for FlexIO, you will see all these examples, but this one in particular is very aligned to making a FlexIO project a reality and giving you the tools you need to do that. So what does this demo require? This demo, it doesn't require any additional hardware to purchase, but it does require, if you look at the README file, it does require that you connect some jumpers between signals on a header that is on the Freedom KD2F. And so the reason is because certain FlexIO pins are used to generate the I2C data, and that I2C data needs to be physically connected to the accelerometer. And so if you go to this, if you download the SDK as directed, go to this demonstration folder that I showed in the previous slide. In the README file, you will see the directions to connect J12 pin 3 to J12 pin 15 and J12 pin 4 to J12 pin 16. And again, this is to get the FlexIO D5 or the FlexIO 5 pin to the PTA2, which is the I2C signal connected to the accelerometer, and the D6 signal to PTA1, which is the SDA signal connected to the accelerometer. So this is a hardware configuration. But looking at that, we wanted to show some capability around the FlexIO and show some flexibility we have on the module. And so if you look at the schematic of the Freedom KD2F, this is an excerpt of that schematic. You will see that the accelerometer, which is shown as the IC in the middle of this diagram, is actually connected to PTA2. And if you look at the pin multiplexing of the PTA2 pin, you can see it also is a FlexIO pin. It is actually FlexIO D12. And so using the pin multiplexing, we can utilize the FlexIO D12 signal as the SEL, or the serial clock signal for I2C. And FlexIO D11 pin is also on PTA1. So just to demonstrate the capability of the FlexIO, we can take this example that is already in the SDK. It works right out of the box to demonstrate the FlexIO interfacing through I2C to the accelerometer. But what if we optimize it in some way and use the pin multiplexing so that way no hardware configuration is needed? And to give you some direction or some example on how to do that, let's look at these C code excerpts here on the left of this slide. Before, the original demo was using FlexIO D4 and FlexIO D5. Those commands are commented out in the definitions, and we simply add 2 new commands to use FlexIO D11 and FlexIO D12 by these defines. And we also have to change the pin multiplexing to set PTA1 and PTA2 to utilize the FlexIO multiplexing option on the device. And so what this allows, so taking that original demo, but enhancing it in a way, this allows that the hardware configuration is no longer needed. So these connections from J12.3 to J12.15 and J12.4 to J12.16, these are no longer needed because we were able to utilize the multiplexing available on the KD2F chip itself and update the firmware with just 4 new lines of code by changing the defines to use the right FlexIO pins and updating the pin multiplexing. And this demo will operate in the same way without having the external connections. And so this gives you some idea of what you can do with the flexibility of the FlexIO. So expanding upon that, I want to give you some picture of where all do the FlexIO pins, there's up to 32 pins if you recall, where all do these pins reside on the chip and where do they reside on the board? And so if you have a look at this slide, on the left hand we have a diagram for the 100 LQFP version of the K82, Kinetis K82F MCU. And you can see all the pins highlighted here on the top, on the right, and on the bottom within the pin multiplexing, which is options for the outputs of these pins. You can set FlexIO signals. And so there being 32 FlexIO total signals available on this KD2F MCU, these are the ones that are actually available on the 100 LQFP version. And what that translates to, on the right-hand side, we have an excerpt of the Freedom K82F schematic. And here, highlighted again, are all the places where the FlexIO signals actually go on the board itself. And so you can see across the platform compatibility headers to be Arduino compatible, we have very many signals that are digital signals, for example, I2S signals, but they are also FlexIO signals, whether they be the FlexIO, the Arduino D5, D6, D7 at the top, all these signals, or the I2S or SPI signals on going to the Arduino header. The point of this is to demonstrate that just like we showed in the updated example case, the FlexIO actually goes to very many places on the chip. This is shown on the left. And that translates to very many places in the Freedom KD2F board itself. And so this platform that we have is giving you many options besides a specific FlexIO header for the camera, which is on the board, also expansion through the Arduino form factor connectors shown here on the right. So all these signals shown on the right go up to the Arduino form factor headers and can be utilized for your innovation around the FlexIO. So what does that mean in terms of possibilities? And wanted to show a specific case leveraging the Seed Studio Grove system. And so I put some links here, but when you talk about creating smart devices and your innovation for these contests, I've seen already many of the ideas depend on the sensor interface. And so the Grove environment with all these different sensors and all these options that are highlighted here is a great way to expand your Freedom KD2F into capabilities, whether it be a gyro or a simple RF kit or so on. You can see there are all sorts of Grove sensors that fit into the Grove base shield. And so the main direction here, or example here, is of course we can do things with the Freedom KD2F all by itself, and we've demonstrated we have an onboard sensor, but perhaps your idea has to do with more sensors or different types of sensors. And one option, there's some other options out there of course, but one option is leveraging the Grove base shield and these Grove sensors that are really easy to interface to. So let's have a look at the base shield and where the FlexIO can be utilized. Again, on the left we have the Freedom KD2F schematic, and you know the FlexIO goes to very many places, but it doesn't go to every signal on the board. And so what that translates to is this diagram on the right. If you look at the Grove Shield baseboard, all the signals, the connections highlighted in yellow, are FlexIO enabled. And so I2C, these all share the same I2C lines because I2C is a multi-drop bus. And so all of those are supported with FlexIO. But besides the I2C, you have the connections for D4, D3, D2, D6, and D5. And one great thing about the Grove sensors is their pinout. Their pinout is standard, and so you can see, if you look closely on the board, you can see it simply has a ground, a VCC or the power, and 2 pins. If it's I2C, then the 2 pins are the SDA and SCL signal. If it is data, raw digital data, then the 2 pins are D5 and D4 for the case of the D4 connector. And so one important aspect of understanding the value of FlexIO is around how these connectors can be used in the Grove system. So whether your Grove sensor is UART based or I2C based, you can plug it in to any of these connectors highlighted in yellow, And because the flexibility of the FlexIO, if you're a UART, you can plug into an I2C header in this shield board, and just by software interface to those pins as a UART. Or if you're UART, you can use the D4, D3, or D2 signals, or plug in an I2C sensor into D4. And so if you wanted two separate I2C buses, so all the I2C on this shield board, they're all connected together, but perhaps you had a system where you wanted a separate I2C bus for separate sensors. Well, the great thing about FlexIO is there on the D5 and D4 pins, you can create an I2C just by the software configuration of the FlexIO. So just to summarize and recap, we're looking at enabling you with examples to expand your capabilities with the Freedom KD2F to drive your ideas to design. And a great enablement is this Grove shield board. And it's not constrained by the definition of the shield board. Because of the flexibility of the FlexIO, you can actually interface to all types of, whether it be UART, I2C, or raw digital interfaces on all of these highlighted connectors. So let's talk about a specific example project that we have made using two Grove sensors. We use the Grove I2C Touch and the Grove Buzzer. And so these are hyperlinks, so you can find more information on these two sensors. But this example project that we have done uses FlexIO I2C master communications with the Grove I2C Touch. And so this touch sensor, which is interfacing to the shield board, is a I2C driven touch sensor. And we can interface that to see which of these 4 touchpads has been touched. Besides that capability of just interfacing to the sensor, if you recall from the Part 1 webinar, once you get FlexIO data in, there's logic and state machine mode capabilities. And in this example, we use the match continuous mode to detect touch patterns. And so the match continuous mode of the FlexIO streams in data into the FlexIO, and if a certain value is captured in this stream of data, it will toggle a status flag into the FlexIO itself. And so this allows you to do pattern recognition. And then the final aspect of this example is we use a FlexIO timer output to set an alarm. So the idea behind this demo is if a certain pattern of touching of the touchpads is recognized, then we'll set off a buzzer alarm with this demo. So this is, again, showing how you can expand beyond the hardware that we have available, the Freedom KD2F, leveraging sensors and showing the capabilities of the FlexIO to do various uses. So we're going to have a document to walk you through this project, but I'm going to give you some preview on how this is done. And one of the first steps is to create a new SDK project. And so if you follow on this link, a prerequisite of this, of course, is that you've already downloaded the SDK that we discussed in the beginning of this presentation. You have this SDK downloaded, then you go to this website for the Freedom KD2F. You click on the Getting Started, and there will be a screen to allow you to get the project generator tool. And once you get this project generator tool, you can create a new project. This will create a folder in your SDK that allows you to create a new project. So what are some important resources for creating this demonstration to create this example? I mentioned already a very nice out-of-the-box pre-built SDK example for the read accelerometer value transfer. And if you look at this software, it is a nice framework for the new example demonstrating how to use the I2C master APIs that we have for the FlexIO. So this will give you some example on what data needs to be sent and what formats to do I2C communication. Besides that, when you talk about using the Grove sensors, there's libraries available. And so if you go to this link for the Grove I2C touch sensor library, there's two files there that you can leverage to accelerate your design as we'll demonstrate in this project. One is the header file for the sensor itself. This is the MPR121 header file. This is giving you all the defines for the registers and commands that need to be sent to this sensor. And the other is a example configuration of the touch sensor itself. So the Grove sensors, they come, many of them come with libraries such as this, and you can see the string of commands or how data needs to be sent to the sensor in order to generate proper communications and interface to that sensor. And so what this actually looks like is shown here on this slide. So if you look at this on the left-hand side, this was a file downloaded from the library for the Grove I2C touch sensor. And the command interface and APIs are different, but the great thing about these files is it gives you a nice setup function. And so the setup function is writing all the control registers, setting up the filtering and the thresholds, so that way you can utilize the touch sensor that's in the Grove system. And so what you have to do to create your SDK project is you can reference this file on the left, file shown on the left, which is showing what data is being sent to which registers, and translate that into the FlexIO I2C master APIs. This is shown in the code on the right. And so you can see that the command interface is different, but the string of commands and the sequence and the data that needs to be sent, you can greatly leverage information that is already posted in the Grove I2C touch sensor libraries and get accelerated on your design there with how to set up this sensor. So very important resources, again, whether it be from the Grove I2C library or from the Kinetis SDK, you don't have to start from scratch. There are some references and files you can leverage in order to do your projects. So let's talk about the hardware connections. We have the Grove buzzer and the Grove I2C touch. And these are connected in two different places. The Grove buzzer is connected to the D3 connector, and the Grove I2C touch sensor is connected to the D6 connector. And I've already mentioned once before, D6 is not labeled as I2C. It is not the I2C bus for the Grove base shield, but because we have flexibility in the FlexIO to emulate on different pins functions like I2C, this is a great demonstration of that, in that even though these pins are not labeled I2C, using the FlexIO we can interface them as I2C pins. So let's talk about the Grove buzzer. The Grove buzzer is the signal that turns on or off the buzzer is Arduino D3. And so looking at Arduino D3 and the schematic we have for the Freedom KD2F, this D3 signal is connected to PTD0 of the KD2F. And then looking at the KD2F pin multiplexing, we can see that this is actually FlexIO pin 22. So the point here is there's some translation that needs to be done at the hardware level. You need to understand these hardware connections. The D3 signal is what is actually physically connected to the buzzer. That's physically connected to the D0 pin of the KD2F. And then each pin in the MCU has pin multiplexing options. And the pin that the multiplex option that is associated with FlexIO on the PTD0 is pin 22. So this is all relevant and important information for creating your software that connects to the Grove I2C buzzer. I'm sorry, the Grove buzzer. Now the I2C touch is connected to different pins. So if we look at the connector labeled D6, if you look closely, you can see D6 is connected to Arduino D7, which is connected to the PTC9 of the K2F, which is FlexIO pin 17. And this will be the SDA signal, and we have the same translation for the clock. The clock is going to be generated on the Arduino D6 signal, which is connected to K2F PTC8 and FlexIO pin 16. So the concept here is there's real physical connections that you need to understand, where you place these sensors on the Grove Shield board, and those get physically connected to MCU pins, and then in the software level you can set FlexIO functions on those pins. And so this is all relevant information that gets translated into defines in our software. And so tying those physical connections to our software, you can see the defines we have on the top left. You can see that we have the I2C data pin is connected to FlexIO pin 17, the I2C clock pin to FlexIO pin 16, and the buzzer to FlexIO pin 22. And then another essential piece or thing that you need to do in order to complete this interface is set up the pin multiplexing. So again, here you can see at the top configuration for port D0 and at the bottom the configuration for the port C. So physical connections that get enabled by software, these are very important aspects of this demo, understanding where the FlexIO pins are physically connected to, which ones are being used, but leveraging the software that we have in place greatly reduces the complexity of doing this. And there are other defines in this demo. So we talked about the SDA and SEL pins and the buzzer pin, but we're also, if you look at the SDK examples, there's defines for other clocking and baud rates and the address of the touch sensor. So all this is handled at the software level, and for this example, it takes some development to do, and we'll be publishing a quick start guide on how to do this. So what does writing a touch register look like? And so part of the SDK examples, whether it be this example that we created leveraging the SDK, or the SDK examples out of the box, they use this write API for I2C master. And there's some specific framework that needs to be followed in order to use this software. So we define the structure for sending I2C data. And this includes the slave address, the direction of how you're sending that data, the register that this I2C is to be read or written to, the sizes of these data that you are sending. So the key point of this slide is to give you some idea of what the I2C, FlexIO I2C master write API looks like. And so if you know your slave address, how much data you're sending, and which register you're writing to, all of this gets utilized by this driver that we have in the FlexIO. But you have to format the data in the right way to use this software enablement. And the read I2C is very similar. It has the same structures and a very similar interface. And so to recap, whether you start from the SDK that you can download for free as directed in the beginning of this presentation, or you're building from this example, this is the same API, the same software interface that we will have for either case, and it consists of this information, the slave address, direction, and so on, that allows you to interface to I2C sensors. So besides the I2C interface, we wanted to demonstrate some other capabilities of the FlexIO. So if you recall, the FlexIO can be used to shift in and shift out data, but there's also logic and match and state machine capabilities. And so what we wanted to build for this example is a pattern recognition case where we can recognize when all the touch pads are being touched. And so there's, in order to do this, there's a shifter setup that is shown on the left and the timer setup that is shown on the right. And there's a match data and mask that is shown on the bottom. And so to set up the timer, the shifter is where the data from the I2C SDA pin is going to be passed in. And you can see two important configurations of this shifter are which timer it's associated to and also which physical pin it is associated to. And so the shifter is associated with the I2C SDA pin because this is where the data is going to be coming in and this is the data that we want to monitor. And the timer that is associated with this shifter is the timer 2 because this is the timer that we're going to use to control how that data is shifted in. And the configuration for the timer is shown on the right. And on this, some important configuration for this timer is what is shifting in the data. Well, it's I2C, so we have highlighted the FlexIO clock pin as the source for shifting in that data. And then another important aspect of this timer setup is the amount of data shifts. How much data are we shifting in? And that is set up there. So again, we're using timers and shifters to bring in this data and we want to monitor it. And the way that is done on the FlexIO is by setting up a match data and optional mask. And so the interface to this sensor is such that when the pads are touched, they read as a logic 1. So if we want to see if 4 pads are being touched, we will set up a match value as is shown, highlighted by this match data of F000. And if we want to concentrate and only monitor that most significant byte, then we can use the mask build to only monitor the F0 portion of that match data. So this is demonstrating how the shifter and timers are set up to work together to bring in the data, and then what match data and mask are utilized to monitor when we have 4 touch pads being touched in this example project. So once we get that match, there will be a status flag generated by that shifter. And so in order to do some pattern counting and alarm generation, we utilize another timer, in this case the FlexIO timer 3, and we monitor the status of the shifter that is bringing in the data. So the previous slide showed the shifter 7 configuration that is bringing the data and checking it with the match capabilities, and now this is showing the timer 3 and how it is set up in order to count how many times those matches occur, and also to generate an alarm by having a associated output pin. And so the important aspects of this configuration for this FlexIO timer are that it is the trigger is coming from the status of the shifter that is doing the match. That's the shifter 7. The pin that is associated with this timer is the buzzer output pin. So once the timer times out, it will toggle that pin. And then the way this timer is decremented, or what it is counting, is the amount of triggers. So the previous slide we showed how to set up the shifter to do a pattern recognition for a certain touch pattern. And then this is showing how to set up a timer to monitor that pattern and count how many events have occurred. And so at the very bottom of this configuration on the left-hand side, you can see that the timer compare value is written to 1F, and this will be how many times the number of touch events that match that pattern of all the touchpads being touched. And so this goes beyond just a simple yes or no touch pads are being touched. This allows you to recognize a specific pattern of touches and also count how many times that pattern has occurred. So just to restate the steps, the sequence of events associated with this is that each time a match occurs, a trigger is generated by the timer by the match shift register. The timer is set up to create the signal on the buzzer pin, and the timer is set to decrement for each trigger. And when the compare value is met, then it will toggle the buzzer pin, and you'll hear an alarm in this case. So just a reminder, we really are excited about all the ideas we've seen, and whether you're here to learn more or you're thinking about entering an idea, we really want to direct you to this challenge and get you started flexing your mind to participate in this challenge. And that's the presentation for today, and we hope you enjoyed the session and look forward to seeing your ideas.
Great, thank you so much, Donnie. I hope you all
Thanks, Donnie. Adam, are you able to address some of the questions that we've come across?
Absolutely, yes. You guys can hear me?
Yes, I can hear you.
Awesome, great, wonderful. Okay, so I'm going to go through the list of questions. Give me 1 second here. The first question, when we talked about it was actually early on. You mentioned the SDK, and the question is it available for the Mac? And I think you might be on mute, Donnie.
It's downloadable for Windows and Linux, not Macintosh, so you'll have to run some Windows emulator.
Got it, so through an emulator, okay. The second question was, well, there's actually a question which maybe it's a bit confusing. The cost of FlexIO, which is really an integrated module with a Kinetis board, right? So would you like to kind of explain that, the relationship again, FlexIO, Kinetis boards? Yeah.
Cost is an important parameter for MCUs. You know, we're really on the edge if you think about edge nodes in IoT environments, and cost is a key factor to MCUs. And the great thing about FlexIO is it's becoming standard peripheral, and we already have it integrated on the KD2 and KL82 and a handful of other devices. So from the end user perspective, it's part of the cost of the MCU, and it's becoming a standard peripheral for us because of the benefits it brings. So really the cost is abstracted in that way. I think if you're doing sort of like a benefit analysis, the benefits of this module are really, we hope the users can recognize the value it brings to time to market, increasing power efficiency, offloading the CPU, and generating some fast control responses because they can do things without the CPU. And so a lot of benefit with almost, I mean, the cost is abstracted because it's part of the MCU cost.
Awesome. Great. Thank you. Here's another good question. Does a clock feature of FlexIO that allows to sync serial data on another pin to a shift register can be reconfigured on the fly?
So a lot of the capabilities of the FlexIO only require a subset of the FlexIO registers and functionality. So there are 8 shifters and 8 timers in the Freedom KD2F FlexIO implementation. To do I2C, it takes 2 shifters and 2 timers. So there's a remainder of 6 shifters and 6 timers that can be used to do other functions. So I think that for the case of reconfiguring clocking, probably what would be more feasible or easier to implement would be, hey, use a different, instead of trying to on the fly change the clocking associated with a certain FlexIO function, you can just have incremental shifters and timers to do that function. And so in that way, you use certain shifters and timers for function 1 and different shifters and timers for function 2 that operates at different clocking.
Great, got it. There's another question in the queue that I was trying to clarify. Okay, so there's a question about Windows 10. Is everything flexible, compatible with Windows 10, your SDKs? I'm trying to verify whether the question is Windows 10 IoT Core running on the MCU or not, and I think the answer is not. But just in case I'm getting it wrong, is everything compatible with Windows 10 or previous versions of Windows as far as the SDK?
I do not know that answer. I don't use Windows 10. We can follow up and make some stuff about that.
So I happen to know the person who asked the question, so I'm going to follow up directly.
Oh, awesome.
Great. There's another question from Tamara. Can you share some other ideas in which FlexIO is being used? Let's see. One of the examples was the buzzer and camera, but she's curious to get even more elaborate projects, so more the like I said, the baseline projects. What else can you do with FlexIO and this MCU? You can elaborate.
Yeah. So we've had implementations of RGB display. We've had controlling LED drivers to drive a LED type interface, like mini LEDs. We've had some motor control, some simple DC motor control, because there's so many timer capabilities and pins associated with FlexIO. It can do some servo motor use cases. There's anything that has to do with input and output. One idea that I haven't actually seen but has been mentioned is a digital microphone interface to take in the PDM data and use software to translate that into digital microphone data. So those are a few, and you know, have a look on the Hackster.io ideas pages, and you can see some thoughts there. All sorts of sensors. So the thing that we highlighted today is, you know, many sensors that are out there, they have a standard interface, whether it be I2C, SPI, or UART, and so those sensors can enhance your ideas or your submissions, and you can leverage other sensors out there because the FlexIO can support these standard interfaces.
Great, and like I mentioned, we're actually going to upload this week the first finished project, complete with schematics and source code and pictures and a full story. And feel free to look into that. We'll send it to all the participants of the contest. And you can also ask questions on the page. You'll have a little FAQ area, and you can talk to the engineer who built it. His name is James. And we asked him to help. He's a EE, and he can actually help you learn from everything he's learned from working with this platform. So with that, I think that we don't have any more questions. So I'd like to thank Donnie and thank everybody on the call. This webinar has been recorded, and we will post it to the site sometimes today or tomorrow. And Donnie, do you have any other closing remarks?
No, just thank you everyone, and flex your mind and join the challenge.
Awesome. Great. Thank you very much, everyone.